We'll explore how quantum technology is reshaping the future of connectivity and security for businesses. So Wim, can you tell us more about what exactly quantum technology is and what should businesses be excited about?
Yes, sure, Thomas, and also on my behalf, good morning, everyone. So when we talk about quantum technologies, there are mainly three subdomains that we need to look at. The first subdomain is quantum computers, and quantum computers hold the promise that it will be able to solve certain type of problems that we are not able to solve today, not even with the most actual supercomputing power capabilities that we have. The second domain is quantum networking, and here the long-term goal is to go into a quantum internet that will link together quantum devices like quantum computers in a fully secured way. But we are not yet there. What we can do today is quantum safe communication. And the third area is about quantum sensors, and these sensors are much more precise than the ones we know today, and they can measure tiny fluctuations in, for example, the gravity fields, magnetic fields, or motion.
Very intriguing domains, Wim. But please, can you give us some practical examples to illustrate?
Yes, sure. So these quantum computers, they can solve certain types of problems, structured problems that are highly complex. For example, simulating quantum mechanical systems like we find in biology. Or it can be used to help us in new drug discovery or new battery technology.
All right, so you mentioned quantum computers. How do they look like? Can I buy one?
Yes, you can, Thomas, but they are not exactly cheap, and they don't fit easily in your backpack. Luckily, you can use them via the cloud, and they look like hanging fridges, big cylinders, and these are needed because these computers need to be cooled down and also shielded from interference of the outside world.
But then what makes them so special, so powerful?
Yes, so we all know whatever you do on your laptop in the end is translated into bits, and a bit can be a 0 or 1 at a specific moment in time. Now, quantum computers, they work with quantum bits, or qubits in short, and they have two specific properties. The first one is that a qubit can be 0 and 1 at the same time. It can be, more precisely, a linear combination of its basis states of 0 and 1. Next to that, you can also combine qubits together in such a way that whatever is done on the first qubit has an immediate effect on the other qubit, no matter how far they are apart. And these two elements makes the power of quantum computers.
All right, thank you, Wim. So far you've explained a lot of positive elements, but are there some downsides?
Yes, unfortunately there are. One of the things is these quantum computers can solve very complex problems. One of the complex problems is a mathematical problem that underpins cryptography. And that might be a huge problem, because cryptography, it's all about trust. It's about ensuring that your data can only be accessed by people that should have legitimate access. So when computers will be able to break them, we have a problem, but it will impact websites, digital transactions, digital signatures. So you need to prepare. All organizations need to prepare for this. And there will be a push probably from regulation, but also from, for example, insurance companies and from certain regulation bodies.
All right, thank you, Wim, for that. So to summarize, quantum computers may become super powerful computer that can calculate ultra fast. They have positive application in many different domains, but they also pose significant threats to current cryptographic methods, and they will eventually have the capability of breaking many of today's encryption methods. So Tom, in simple terms, could you please explain how encryption works today and why we should be worried about the impact of quantum technology?
Yeah, sure. Basically, encryption is a method to turn plain text into encrypted text in order to prevent users or unauthorized users to get access to your data. And to explain this, I would like to introduce two personas, Bob and Alice. Does anyone know Bob and Alice? Yeah? Okay. Very good. I can see that there are some people with security knowledge in the room. Welcome. So our Bob and Alice, they work at a bank. Bob works at the regional bank office and Alice is based in the headquarters. So Bob wants to send a message to Alice. But there's another person. Anyone any idea? Eve. Yeah, there. Eve. Eve from eavesdropping. So Eve is going to try to intercept the message. So let's see what happens. Bob makes his email. The bank uses asymmetrical encryption. So they use a public and a private key. The private key remains with Alice and the public key is shared with Bob to encrypt the message. Then they send the message across. Eve intercepts the message, but she cannot read it because it's encrypted. And then Alice will use her private key, her decryption key, to decrypt the message and to read it.
All right, thank you very much, Tom. That's very clear. So now we understand asymmetrical encryption, but what does it have to do then with the calculation power of quantum computers?
That's actually a very good question. So we have a private key and a public key. To calculate the public key, we introduce a difficult mathematical problem. If you look at RSA, for example, there we use prime numbers and we multiply them. This is an example, 3 and 7, two prime numbers, and a prime number is a number which can be divided by itself and 1 only. So if we multiply 3 and 7, we get 21. That would be our public key. If I would ask you, can you factorize 21? I think most of us could figure out that would be 3 and 7. And so would Eve. In reality, we use very large prime numbers. This is the decimal notation of a 1024-bit prime number. So if we multiply this number, we create a public key. This is a 2048 RSA key in a decimal notation. Alice cannot decrypt this. Anyone in the room can decrypt this? You would be the first human quantum computer if you could do that. So if Eve uses the current compute power to decrypt this key, it would take her 1,000 or million years to do that. If she has access to sufficient quantum compute power, it would take her hours or days. And that would mean that all these applications would be at risk because they all rely fully or partially on asymmetrical encryption.
Wow, that's very impressive. So to summarize, quantum computers may decode messages that traditional computer would not be able to do. It seems that the power of quantum computing is rather important, since you mentioned it a couple of times before. Wim, can you please explain to the audience what we mean by powerful enough quantum computers, and when do we expect that to happen?
Yes, so Thomas, when we talk about the performance of a quantum processor, we need to look in essence at 3 elements. The first one is how many qubits this quantum computer has. If you want to solve complex problems, you need a huge amount of qubits. The second one is quality of the qubits. You should make sure that they don't decohere rapidly, but also the way that the operations, the gates, are implemented on the quantum computer. The last one is speed, because these qubits have a short lifetime. You need to be able to do as much calculations as you can per unit of time. Now, to answer your question on when we may expect this, I would like to introduce a graph. And this graph was published last year by a professor from the Waterloo University, Sam Jacques, and it has on the x-axis the number of qubits and on the y-axis the error rate of a quantum computer. Now, today we are in the red zone. That indicates the current capabilities of quantum computers. It is expected that in the years to come, the amount of qubits will go up, as will their coherence time, and the number of errors will come down. Now, in order to break RSA, as Tom explained, we need to be more or less over there. So that's still a huge way to go. And the question is then, how long does it take to go from where we are today to that capability? We don't have a crystal ball. We don't know for sure. Now, there was a publication last year from the Global Risk Institute. So they had an interview done with specialists in this matter, and half of them estimates that there is a 50% chance that these computers, these so-called crypto-relevant quantum computers, will exist in 15 years from now.
All right, Wim. So if I understand correctly, it will take some time to develop a powerful enough, faultless, fast quantum computer. But then, what is the urgency? Why are we here today?
Yeah, Wim is right. It will take 5, 10, 15 years to develop a powerful quantum computer to break these keys, or to enable Eve to break these keys. But the actual problem is store now, decrypt later. if Eve would be able to store data now, sensitive data now, today, and decrypt it later when the powerful quantum computer is available, that's where we have a risk. And to calculate that risk, there is a simple formula. And therefore, I would like to introduce a professor, Professor Michele Mosca. He works at the He works at the University of Waterloo in Canada, and he made a formula to calculate your risk. And the first question is, how long do your data need to be secure? The second one is, how long will it take to develop powerful enough to implement a secure solution into your current infrastructure? And the third one is, how long will it take to develop a sufficiently strong enough scale quantum computer? All right, so to work with, we have three parameters: the shelf lifetime, the implementation time, and the quantum development time. If we look at the formula, if the shelf lifetime plus the secure solution implementation time is bigger than the quantum development time, then worry. So you all have a credit card. If you look on your credit card, there's an expiry date, and that expiry date is actually your shelf lifetime. So if you fill the formula, a credit card has a typical shelf lifetime of 5 years. It will take about 5 years to replace all credit cards in Belgium or the world. And the quantum development time will be somewhere between 5, 10 or 15 years, so we take 12. So for your credit card, you're safe. If you look at your personal data, your basic personal information, it needs to be safe for at least 10 years. So 10 plus 5 equals 15, that's already a problem here. And now we look at your healthcare data. Your social security number needs to be safe for 30 years. So there's a problem already. If you store this data now, and you decrypt it later, that can be a big problem. And if you look at state secrets, that's about 100 years that they need to be safe.
Okay, thank you, Tom. So to summarize, not only we need to be aware of how long our data should be secure for, but we also need to consider the implementation time of a secure solution in the current infrastructure.
Yes.
So Wim, can you please enlighten us on any government recommendation? What are the regulators saying?
Yeah, indeed, Thomas. So the regulators, they are aware of this problem. So in April this year, the European Commission issued already a recommendation to all the member states that they should start working on a transition plan. So that's a recommendation to the member states. There is also publications, handbooks available by different security offices in the Netherlands and in Germany, for example, that explain what the threat is exact in detail and how you should or could prepare. And in the US, the National Security Agency published its second generation of so-called commercial national security algorithms that introduced this quantum-resistant cryptography. They also added a timeline to that, and when we look into detail into that timeline, we see that for a couple of categories, 2 of them, this use of quantum-resistant algorithms should already be in place by 2030, and the rest by 2033. They also announced recently that RSA will be depreciated fully by 2035. So indeed, this may look a timeline, and also it, by accident or not by accident, but yesterday the Belgium Center for Cybersecurity issued, together with 17 partners in other European member states, a joint statement in which they urge everyone to start the transition now. And they have a point, because in the US, the US government did already a first analysis of what it should take for the federal institutions to migrate to a post-quantum world. And it will not be a free lunch. It will take them more than 7 billion and around 10 years in order to complete the migration.
Right, Wim, thank you. You gave us an overview of what's happening internationally, but do we have any idea of where we are in Belgium in terms of quantum preparation, and what can businesses do now?
Yes, indeed. So the question here is how to start with this migration. The first thing is to be aware, and sessions like this, we hope that they shed some light on the problem that is ahead. But in Belgium, we also have, since beginning of the year, an initiative called the Quantum Circle, and the Quantum Circle is really about raising awareness and also interest in all the different quantum technologies. There are already more than 50 companies that are member of the Quantum Circle, and they did recently a survey. And from that survey, we learned that more than 60% is already busy with exploring quantum technologies. So that's the first step, awareness. Then the second step, you need to prepare. How do you do that? First, you need to look at your inventory. You need to look at which crypto is used where in your environment and build a kind of so-called cryptographic bill of material. Yeah? You also need to introduce crypto agility, because the new quantum resistant algorithms, they're quite new, and they may still change a bit over time, or new ones may be introduced. Crypto agility is also key. When you've done your internal homework, look at your supply chain. Yeah? A supply chain, or a chain in general, is as weak as the weakest link. Yeah? So you need to check with your vendors how they are preparing, what their roadmaps towards quantum safeness are. Then thirdly, risk assessment. Based on your data, how critical is your data, and what is your most critical data, how long does it need to be secured? Once you have a good view on that, and also here take into account any systems that cannot be made quantum resistant, because for these legacy systems you need to replace them, phase them out. Once you have this done, you can build your migration plan. This concludes the preparation phase, and then of course you need to execute, and at regular intervals check whether or not the assumptions that you took in the previous steps are still correct.
Right, thank you, Wim. So we understand that due to the store now, decrypt later issue, we need to act today. Tom, what solutions are available today in terms of encryption?
There are basically 3 solutions available today. The first one is symmetrical encryption. The second one is quantum key distribution. The third one is post-quantum cryptography. So we will have a deeper look into the 3 domains, and we're going to do that with an assessment on readiness, implementation, on quantum safety, and on cost. So low is challenging, high is good, red is challenging, green is good. So if you look at the cost, I presume that you all like cheaper solutions above expensive solutions. So if the cost is green, it is cheap. All right. Let's have a look at the first one, symmetrical encryption. Symmetrical encryption basically is implementing a key on both sides of the link without exchanging it, and using 2 keys on both sides. This solution is considered safe today. It is ready. It is.
Tom, let me interrupt here. Why is symmetrical encryption considered quantum safe?
Oh, that's very good. Very good question. So symmetrical encryption uses another algorithm, AES for example, and AES can be attacked by a quantum computer, but the quantum computer, when it's powerful enough, will only be able to cut the difficult question solution time in 2. So if you divide 1,000,000 years or 1,000 years by 2, that's still a very long time. That's why it's considered safe.
Okay.
But you can see an exclamation mark here, and that's because you have to safeguard your keys. If you have a large complicated key and you give it to someone to implement it, then he has the key. So the solution for that is to implement a solution with an SMS.
Yes, interesting.
No.
Check my
No, don't look on your phone. Okay. It's a security management server. It's not an SMS.
Okay.
So an SMS is a way to safely create and distribute your keys to the systems to use asymmetrical encryption.
All right. Tom, this seems a bit too theoretical to me. Would you have some practical use case to illustrate this concept?
Yeah, let's go back to the bank. A bank has a lot of regional offices, headquarters and data centers. We can easily add a symmetrical encryption solution to the existing asymmetrical encryption. And while talking to customers about this, we bumped into a particular new use case, and that is a rapid response kit, and we see interest to use this kind of encryption methods for marine, for critical infrastructure. What if the network to manage your critical infrastructure goes down, then you need to get a new connectivity up as quick as possible, and it needs to be safe. And the third one is non-governmental organizations who have operations in dangerous areas.
All right, thank you, Tom. That was the first solution, symmetrical encryption. What about the second one, Wim?
So the second one is quantum key distribution, or QKD in short, and this uses quantum mechanics to distribute keys. How does it work? There are a couple of different implementations, but one that is often used is the one that uses polarized photons. So you have there on two sides, you have these quantum key distribution that send over a quantum channel, which is typically a dark fiber or free space, polarized photons. And based on these polarized photons on both sides of the line, the same key is generated. And this key is then used by the encryptors in order to encrypt the data that go over the normal data link. Now, from an information theoretical point of view, this solution is quantum safe for eternity. It cannot be broken, not even by the most powerful quantum computers. There are some downsides, however, they're quite costly. They have still some limitations in the distance that they can cover, and it's a new technology, so we still need to learn and adapt a bit on it.
Same question, Wim. Any particular example you would like to highlight?
Yes, so Proximus already last year did tests with it. We also deployed it on a production link between our two data centers in Everen and in Mechelen, and the data that was sent over that link was encrypted with these quantum keys. Of course, we are following up all the evolutions that take place in this area.
Okay, so what about the third one?
The third one then is post-quantum cryptography, or PQC in short, and these are new mathematical problems. They in essence replace the asymmetrical cryptography that we know today. So it's new, it still needs to be implemented, but they are at least published. So the National Institute of Standards and Technologies published the standards, and the vendors are now starting to look how to implement this post-quantum technology into their different solutions.
Thank you so much, guys, for presenting the three solutions. Sadly, we arrive at the end of our presentation, and here are my key three takeaways. One, quantum computers are coming. They become a reality. Two, there is a cyber threat that exists today, and it's called store now, decrypt later. But don't worry, don't panic. There are some encryption quantum safe solutions available today, so you should start your quantum journey today. Wim, do you have anything else to add?
Yes, for those people that want to stay ahead of the curve and learn about quantum technologies, link up to the Quantum Circle in Belgium. That is the organization that aims really at bringing interest in quantum, knowledge about quantum to a higher level.
Proximus next. Think possible.